Awesome. Right. See how it goes. Yeah, hold on, sorry. Looks okay. All right. Yes, we can start. Hello, good to see you for the first time. So actually, I should ask this question, right? Any preference in terms of classroom like this? Blackboard, you know, like which kind of lecturing style, right? I mean, I suppose that students are okay with, you know, but if someone like to have lecture on Blackboard, you know, because you're here in person, right? What's the point of having this? And you're willing to make the travel. So yeah, I don't know. Just like I said, I want to accommodate everyone. So anyone hates this and you want, you know, more traditional Blackboard lecture type, speak up. I'm very flexible. You're good with this? Yeah. Okay, cool. Yeah, I think it's more flexible anyway, right? But do remember, right, that if you have some discomfort or objection to any, you know, the way we conduct class, let me know. All right. I mean, it's not like I'm imposing a fixed format for you. I mean, I have to follow university protocol, right? But they say in person, right? But you know, whatever we want. So we're all good, right? Make sure that, you know, if you have anything you want, let me know. Okay, cool. Let's start class then. Questions? Actually, anyone mind checking on Zoom to see if it's recording my voice? Because I know that it's writing, right? But if it's not recording my voice, then it's useless in some way. Does anyone know? Just to make sure that, you know, again, so in the future, right? I hope one or two will come to class. Lecturing to an empty classroom is a little bit awkward, but you know, if you have something you want to stay at home, I wouldn't have, right, an issue. Can anyone tell if like my voice coming through? Anyone checking?
Recording in progress.
My voice coming through? Yeah. Awesome, thanks, appreciate it. Okay, cool. All right, you can turn it off if you want. Right. Or, you know, if you want to follow on your laptop, that's fine too. Just put on an earphone or something, you know. Oh, classroom these days, God knows what we're doing. Any question? No question? All right, so let us start with right where we left off last time. So I was talking about, right, the point of modeling a little bit. Right. And I want to caution you that, so the inspiration I draw from, right, is from time series kind of point of view, which is that, you know, you want to model the stable component, right? So let's not even put that in parentheses, not in bracket, but so the stationary, all right, that means it's stable, right? It doesn't change component, right, of whatever that you're trying to look at. So for our stock model, right, for the stock, You can check, or you can, look at experimentally that the price, right, is not stationary. All right, that's very clear. On the other hand, it's reasonable, right, to believe, and again, like, this is why I want you guys to kind of do data, right? Because you will see that whatever assumption the models make, right, you will find some point, sometime, that data, right, violates that. So we'll say that, right? So reasonable to believe that the returns, right, are IID. Now, the point that the returns are IID is more like from our mind, right? We think that, well, return on one day shouldn't have, anything to do with return on next day, right? But of course, so independent actually is reasonable. The identical part, right, is actually kind of awkward, because you have seen, right, with the Yahoo Finance, right, the period of pandemic, the return definitely is very fluctuating, while right after that return goes back to normal, right? So the IID part here, right, has to be verified with data, right? So, right, so we need to, right, so it may be violated, right? And this is why you might want to have a better model, right? So I'll talk about that later, but to capture, right, the fluctuation. So anyway, but for now, also the point is this too, right? You want to know what kind of assumption your model is making, and B, you want to know when it's violated, right? So Black-Scholes, which is what we're going after here, right, assume that returns are IID, and that's the point I want to make, right? If you observe, right, a period of time where returns are not identical, right, the independent reasonably okay, then you can use something like a stochastic volatility model, right? So to capture, right, the change in the volatility. All right, so that's the reason why you can justify that you use a more fancy model than Black-Scholes, because you want to capture, right, that fluctuation you see in the data, that the Black-Scholes assumption won't be met. Okay. Anyway, so we will model, right? We start the modeling from the returns, and then you will build up the stock price from returns. All right, that's the philosophy. Okay, because again, right, it's kind of, I guess, very natural for a student to think that you just want to jump into a stock price right away. You want to play with the stock price, right? From the modeling point of view, that's completely different, right? You start with the returns first, because it's stationary, it's easy to model, and then you rebuild the stock price from that. Okay, so the case in point, right, is, for example, with the binomial model, right? You would want to start with the kind of, the percentage return, right? Or you model the x1 up to xn, let's say, right? IID with up and down, right? And in fact, right, these are, right? So xk, which is 1 plus rk, right? Where rk is the percentage return. Right? And then the stock, right? The stock price will be model reconstructed, right, from the return like this, right? So basically, the point is you have S0 given, right? And then so from S1 is S0 times 1 plus R1 or R0, right? S2, S1, 1 plus R1, etc., right? Like that. Okay, so that's what I mean by rebuilding, right? Rebuilding the stock from the return. Now, this seems like trivial, right? So trivial, because actually, because the model is so easy, you don't see the point, right? Of why do I want to do this, right? Why not just model this directly? What's the difference? Well, that's fine, right? But when it comes to more sophisticated model like Black-Scholes, then you'll see the point that, right? With Black-Scholes, right? Well, I did give you this formula, right? Let's write it out like this. So notice, right? This gives you the stock price, right? This gives you the stock price directly. But when someone look at this, right? it's very, very reasonable for them to ask, why do you write down the stock price like this? What property, right? You want, I mean, yeah, why are you capturing like that, right? Why does the Brownian motion enter like this? Why not somewhere else, right? What's the point? And probably you're stuck, right? Because you don't like, okay, I'm not so sure that's what people do, and that looks pretty cool, right? The stock price looks right. That makes, that's not going to convince anyone, right? So again, right? So why this way, right? In particular, right? I guess this part seems reasonable enough. That's some kind of exponential growth. But right, I mean, how does the Brownian motion enter like that? Right? How does that capture volatility? You understand? And again, right, I would guess that some of us here are not even that familiar with the concept of volatility, right? I mean, what is volatility? And so if you say sigma is volatility, fine, then why does this capture volatility of a stock like that? You understand? So, right, I mean, my point being is that looking at the stock price directly doesn't explain. Now, of course, right, in practice, if all you care is to price an option, then who cares, right? This is the right model. People have been using it. Why question it? Use it, right? But you want to, right, to be able to work on the model, understand how it's constructed, right? So I'm talking about deeper kind of work, so that, right, if you have to modify the model, you know how to modify it, right? For example, if you want to incorporate, right, changing volatility, how do you incorporate it? Right, you're not going to go into this model and say, okay, I'm going to change sigma into like, changing component. That's wrong, because that will violate, right, stochastic calculus, right? You didn't start the model from the ground up, right? You cannot just go into the model and change some piece of, you have to look at how it's built, right? So the reason, right, or the foundation for this model is from the return, right, where we have two flavor. Either you build the percentage return, which is mu dt plus sigma EWT, or you build a log return. I'll explain this later. All right. So this is percentage return, which is clear, I hope, because, right, this is change in stock price divided by, right, the original stock price. Maybe it's not clear that this is percentage return, log return, but actually you see it because the D, right, the D notation means a change, right, delta, if you will, right? D, you can think of it as delta, but this is a differential in continuous time. That's why we write D. But if you want, right, this is really something like this. That's log of ST plus DT divided by log, D means change, so subtract. All right, like this, right? That's D. But of course, when you subtract log, right, that's become log of the ratio, right? And that's why it's log return, okay? Now, so now at this foundation, right, and it's easy to explain what we're trying to, what story we're trying to tell. What are we trying to say, right? We're saying that the percentage return, right, on average has return rate mu and has variance sigma, right? Why? Because now we didn't talk about this, right? But this is where the foundation of the Brownian motion comes in. So this is a normal, right, with mean zero and variance dt. So think of it as like, that the step size of the random walk, right, with mean zero and up and down in symmetrically, right? So let me just try to explain to you, right? So for now, you can think of dwt as IID, right, 0 dt. So we'll look at that later, right? But so if you accept this, then you see that, right? What are we trying to say here? That expectation, right, of the return. Notice, right? This piece has mean zero, right? So we only have mu dt, right? So it's very intuitive that 1 over dt, right, times this is mu. And that's what we're saying, right? We're saying the average rate of return is mu, right? Average rate of percentage return. And if you take the variance, right, then notice that this is a constant, right? So it goes away. This has variance dt, right? So it's going to be sigma square. dt. Again, 1 over dt variance of is sigma squared. And this is the exact meaning of volatility, okay? Variance of return, right? Take the rate, that will be your variance. And of course, if you take the square root of this, that's your volatility. Got it? So, right, again, it's very intuitive like this, right? Of course, you see return, right? It grows linearly, do you see? Because, right, if if you patch the time interval together, then this dt will add up to, the whole 0 to big T. Variance, so return and variance also grows linearly with time, right? So I'll try to show you the math later. But both of this shows you that returns, right, and expectation and variance of returns grow linearly with time. Of course, with different rate, right? The rate of growth of expectation is mu, and the rate of growth of variance is sigma squared. Okay? But again, right, try to think about it. This exactly captures our intuition on, right? Why do we say that a company is doing better if it's higher mu? Well, because as time grows, it will pick up that return much higher because of a higher mu, right? Why do we say a company is more volatile if sigma is higher? Because again, as time grows, right? If sigma is higher, then the fluctuation, right? So here, let me show you something like this, right? Easy. Hold on. Not easy, it's not true. Let me go back, right? So, okay, let me pause. Any question on any of this so far? Okay, right? So maybe let me just say that, right? This piece of writing, right, is very easy to analyze in terms of the meaning of returns. One more thing, right? Notice that we say here is log return, right? Notice how there's a magical piece of -1/2 sigma squared here. Remember, I keep saying that the log return is lower than percentage return, and you see with data that that's true, right? So you will see that the movement from here to here is because of calculus, stochastic calculus. So mathematically, we do capture, right, this change in the way we calculate returns. Okay, that's one thing. Second of all, right, I mean, you can see the same calculation applies here, meaning you can take expectation and variance. Okay, and so what we're saying is, in terms of like doing a different unit of calculation, right? If you calculate percentage return or log return, we have the same volatility, right? It's just slightly different rate because of the different way we calculate, which makes sense, right? The next thing I want to say is this, that I'm a little bit wrong to add things like this. It's kind of okay, but percentage return do not add, log returns add, right? I think you have seen that, right, from the homework. What I mean is this, right? Suppose you have time period 0, 1, and 2, right? So what's the log return from 0 to 2? Log return from 0 to 2 is log of S2 over S0. Yes, that's the return over the whole 0 to 2 period. And that will be what? Well, in terms of log, right, that's just this. Now I can easily do this, right? I mean, there are many ways you can do this, but so telescoping sum, or you can do it the other way around. So basically, you understand? But right, I mean, like, it's very intuitive. If you talk to people in finance, they probably wouldn't even think twice about it, right? So basically, you add the returns over a small period, you get the return on the longer period, right? Except that you have to be careful. You have to do it on the log scale, right? I mean, on a log thing. If you do it on percentage return, right, you wouldn't. It's not right, right? Look back on the homework. The log return multiply, right, and take the square root. That's how you take the average. Okay, take the root. Anyway, right? But roughly, you can just wave your hand and say something. So anyway, because log returns add now, right? I could use this, right? But for the log returns. So basically what I'm trying to say is, right, if you look at an interval from 0 to big T, right, because log returns add, then the log will be this. Does it make sense? Because, right, I have changed the dt to t minus 0. So it's big T, right? But I have done it, why? Because basically you understand, right? Basically that's going to be T1, T2, up to Tn minus 1, right? Each of them has length dt, right? And because log returns add, right? And each of the piece has this kind of expectation, right? So actually, sorry, it should be mu minus 1/2 sigma square, because I'm talking about log, right? Doesn't matter, because it's just kind of the average of log return. But the point is what, right? That you see that the rate of return will grow linearly with time. The variance grows linearly with time. Does that make sense? Because, right, actually here, notice that here, right, basically, now you can go back to this formulation and write like this, right? And of course, right, this piece is a constant. So, well, you know, you can flip it on the other side, right? Right. So what are we saying? What we're saying is, so now you see, because then this is like a, you know, like a intercept, right? This is exactly saying that the average of the log price grows linearly with time. Now you go back to this explicit formula and take the log and see that that works the same way. Understand? With me so far? So I'm trying to explain to you how, right, the return model is consistent with the price. But you cannot work the price directly. You want to work from the returns and recapture the price property, right? But again, so log price grows linearly with time on average. Makes sense? Or actually, you're saying returns grow linearly with time. Log price is just a fancy way to capture returns, right? Same thing, right? Variance of log price. Again, right? I will drop this guy because it's a constant. So variance of constant is 0, right? So variance of log price also grows linearly with time. All right. That's what we're saying. Questions so far? Okay. So that's the point of modeling, right? You understand the model from the ground up. And then the math, right? The math is exactly used to connect these pieces. How do you, once you know what you want to model, right? That's kind of financial thinking. Then you use the math to reconstruct, right? This to here, and then this to here. That's math, right? Math has nothing to do with model. I mean, math has something to do with model, but mathematical thinking won't lead you to sensibly write down a model. You have to understand the financial context, right? No matter how much math you do, you don't understand why, right? Returns have to be IID. That's financial intuition, got it? So that's why I want to emphasize, right? That's different ways of thinking, right? Okay. No question, right? Now, let's talk a little bit about, you know, so last time I kind of waved hand a little bit, right? But I want to bring you up to this, right? So now this one I would think is important because, of course, you know, again, right? The point of this class is to teach you about Black-Scholes model, but I want to at least for you to see that first of all, right? There's a connection between binomial model and Black-Scholes model, okay? The reason is this, that as far as I know, right, in the industry, people still use binomial models for some work. Care to guess why? I mean, if we have Black-Scholes model, why do we still want to use binomial model? Basically, you go to industry, people say, yeah, I mean, yeah, we can use a binomial model to price stuff. Why? If you have some fancy tool like Black-Scholes, actually Black-Scholes not that fancy, it's quite easy to deal with, right? Why do you still use binomial? Two reasons. You want to say something? Okay, so the first is what I want to talk about. I mean, both binomial model will approximate Black-Scholes model, right, with delta t small and n large. So if you pick, right, a lot of periods, then qualitatively, it's kind of close. The calculation between binomial model and Black-Scholes model are close. So in fact, the homework of this week, right, you're asked to kind of verify that with the implied volatility. You calculate implied volatility from the Black-Scholes, but you're asked to plug the implied volatility back to the binomial model and push the number of periods to large to see that it recapture the price. That means that the Black-Scholes price and the binomial price are similar, right? That's the point of that. Second of all, right, what's the advantage of binomial model that Black-Scholes doesn't have? Binomial model is discrete. Discrete model allows you to say at this point you want to do something, at this point you want to do something. Black-Scholes model is continuous. Okay, so if you want to analyze something like path dependent, like exotic option, like hedging, then binomial model, right, with only two options, allows you to write down replication and analyze each point of the path much more easily. And Black-Scholes continuous. How do you analyze, right, the scenarios and space-wise and time-wise? Okay, so binomial model is discrete, so it's convenient of a more complicated option, such as American and exotic. Okay. Did you do American option in 621? Right. And you see how, right, with American option, exactly you have to look at, right, whether to exercise or not at that time point by looking at the next step. If we are in a continuous time mode, what's the next time point? Right? So yes, there are reasons to study Black-Scholes, right? And to do continuous model, but let's not lose track of, right, that it's a good tool, it's a fancy tool, but like I want to emphasize, right, is used in the right time, right point at the right place, right? And a lot of times you want to swap to an easier model for analysis and you want to understand why, okay? So here, right, so first of all, I'll show you the Python simulation, right? Hopefully we'll pull it up on here. But first of all, I want to look at the parameterization, right? So on point number one, right? Let's analyze on point number one theoretically a little bit, and then we'll see the simulation code. On point one, right? There are several things. So parameterization, right? Of binomial model. Now, do you realize this, right? That we are, I haven't talked about this so much because I haven't really, right, go to the concept, but in terms of risk neutral pricing, right? That's what we're in. Can anyone tell me, in terms of risk neutral pricing, right, what's the most important characteristic of risk neutral pricing? I'm not asking about the concept or intuition. What's kind of like the most important characteristic of risk neutral pricing in terms of behavior of the stock? So when you do risk neutral pricing, what do you automatically assume? Or automatically, what mode are you in? So in risk neutral pricing, right, percentage return of the stock is always risk-free rate. Agree? That's the point of risk neutral pricing. Doesn't matter what the actual return is. When you're in risk neutral mode, the percentage return is risk-free. Second of all, what's the volatility? Volatility is sigma, which is the same as the physical probability. The second point, I'm not sure if you have seen it before, or I'm not sure if Professor Larson emphasized that. But it's kind of like a more subtle fact, but it's there. Okay, so I'm sure you know this is the first one, right? The second one, maybe you haven't seen it so much. But basically, what's the deal? So you see, the point I want to make is this, that you might think that return is important, right? Yes, it's important in the real world. But in terms of pricing, guess what piece is the most important? Volatility. Because that almost, at least at the easy level, right, is the entire thing. I mean, even at a more sophisticated level, is the entire thing that drives the model, right? Because our percentage returns always are. There's nothing to model there at all. The risk-free rate is all we have. I mean, of course, if you allow the risk-free rate to be stochastic, then yes, right, this piece will be more complicated, but that's about the, the modeling of the risk-free rate. As far as the stock model is concerned, the volatility is the important piece, not the return, right? Okay, because when we do pricing. All right, so that said, right, now let's go back to the binomial model where you have, right, stock like this, right, and then you go S0U, S0D, right, etc. Okay, so I said last time, right? So what do you want? So first of all, anyone care to tell me? So this is Q, right? And this is 1 minus Q, right? Like that, up and down. Anyone care to tell me what Q is for risk neutral? You remember?
Minus D.
U minus D.
U minus D.
Very good. Except that here I'll use this, okay? I'll use continuous compounding, but yeah, you're right. I would say that it should be 1 plus R delta T because you need to, take into account the time period, right? I mean, unless you assume that the time period is 1, then we don't care, right? So what's the consequence that under Q? So when we write, right, expectation under Q, right, expectation E tilde from at least for me, right, is expectation under Q, right? So what we're saying, right, is E tilde of like E to a minus R delta T, right, S, let's say S1, right, is equal to S0. Agree? That's what we mean. So what we mean, right, is that E to a minus R delta T, right, S0U Q, right, plus 1 minus Q, S0D is equal to S0, or, right, you see S0 cancel out. So exactly, it satisfies this, right? And you see why Q must be that. Yeah, that's what risk neutral pricing is, right? When you take the future, right, stock price, discounting, this is one period, right? You get the current stock price. All right. All good so far? Now, okay, so let me ask you this. What's the volatility in this model? What's the volatility in this model? Well, you just calculate, right? I mean, again, maybe you haven't thought about this, but again, like I said, volatility is the bread and butter of pricing, right? Not pricing itself. So what's volatility? Well, volatility is the variance of the percentage return, right? And it's going to be this. So variance of 1 plus, let's say R1, because they're all the same, right? So which is, right, 1 over delta T, right? So sorry, variance tilde, right? Why variance tilde? Because we claim, right, volatility is the same whether it's physical or risk neutral, right? Again, a subtle point, I'll show you later. Okay, so but what that means is this is going to be Q QU squared, right? Plus 1 minus QD squared minus, right? So that's expectation is square minus the square of the expectation. I could write this as e to r delta t, right? Because that's expectation, but I don't care. Agree? So that's, you understand what I'm writing here, right? That's expectation of the square minus the squared expectation. But of course, right, do pay attention that this is e to r delta t, right? Because of this. So if you want, you can do that. Anyway, the point is, what is this supposed to be? What's this magical, what's a magical parameter here? Is this sigma square? Yes. Question so far? Now, okay, you understand all the connection? Any question? You understand what each symbol means? Do ask question. All good, all clear. I think you do look puzzled, but you don't want to ask questions. All right, fine. I assume that you're fine. So far, right? All these are just symbolic connection, all right? No, nothing's deep. It's really just connecting what we really mean by, right, return, what we mean by risk neutral, what we mean by volatility, etc. Okay. Except, right? Here's the rub. The rub is, like I said last time, if you want to calculate implied volatility, you really want your model to be in terms of sigma rather than in terms of U and D. Why? Think about it. What is the point of calibration, right? What's the point of implied volatility? When you do implied volatility, right, or imply parameters, okay, you want to understand the point of implied parameters. So implied parameters or implied, or you can also think of this as calibration in some way. Calibration to market price. Right? What do? So the activity of pricing is like this, right? You have a beautiful model somewhere. You have a risk neutral definition. You have a risk neutral, right? Kind of scaling. Then, right, you say that VT, right? E to discounting. Again, I'm just writing this. I'm not writing it in the very careful way of the model, but it's like this, right? That's your pricing. And you know, let's do call option to make it more concrete. Okay. Now, what is the piece, right? ST here, right, will be given by your model, right? And like I said, this at the end of the day will be just a function of all your parameter R, T, K, S0. And in this case, right, U and D. Agree? Will be V0. Yes. I mean, it's kind of messy if you write down the thing, right? Because if you have multi-period, wow, you know, whatever, right? But at least abstractly, it's like that. And when we have a computer in front of us, right? Who cares? We just write down an abstract function for a computer, right? We plug in these things, computer will do the calculation and spit out the value, right? By the way, that's how you think of it in terms of numerical analysis too, right? You don't need a analytic function, right? You only need a piece of function that you can calculate, right? The function out, and then you can input that to like a package for it to do some calculation for you, right? In terms of like implied derivative, whatever. In terms of differentiation or solving equation, right? So anyway, the point now is, right, to find implied parameters, what you do is now you set, right? Set this to be equal to the market price, right? And you solve for, what are you solving for here? You solve for U and D, right? Because that's the only piece of your model. That's exactly the parameter of your model that's uncalibrated, right? Everything else, like I said, can be read from the market, like this and this and this, right? These are all from the financial information. U and D, right? You understand? It's from the stock price, which, right, it is nowhere to be read. Is part of your model that needs to be calibrated. And how you calibrate it? By making sure that the pricing equation, right, match the market price. Okay. But do pay attention, right? U and D actually is not of much interest to people. I mean, what's U and D, right? I know that someone says it's up and down, but right, think about it. When you look at a company, again, right, this is a very simplistic model to begin with. If you tell them that this is up and down, it has no meaning. What they want to find is volatility, right? Up and down, because, right, then they'll ask you, why don't you have three choices or 5 choices, right? So if you give me up and down, it has no meaning, but sigma has meaning, right? So then, of course, you could, from here, right, plug that into this formula to find sigma. All right, but that's awkward, right? So these are, right, U and D now will be. So when you do this, right, that's what I mean by U and D are implied parameter, okay? So imply anything is when you calibrate the parameters into your model and it match the empirical price, right? That's what we mean by implied parameters. Now, and then, right, you can solve for sigma, right? But I would claim that this is not elegant. A better way, right? And it also has connection with Black-Scholes. A better way is to use sigma directly. Okay. But notice that's, again, right, I hope you appreciate, even from a modeling point of view, not even from a mathematical point of view, that use sigma directly makes much more sense, right? Meaning that you somehow want to reduce this U and D in terms of only sigma. But I want you to appreciate that, right? This 2 points. First of all, this is a very sensible thing to ask for, even in terms of modeling. And second, right, that it's not that trivial to figure out what it is. Because why? The U and D must satisfy these 2 equations. So the question is to find U and D in terms of sigma, and it still satisfy this equation. Now that's a nasty piece of calculation, right? Because you think about, right, this is U squared, D squared. And if I give you one hour to sit there and look at it, you won't be able to do it. I tried, I couldn't do it. So the point is this: you can look into Hall, right, John Hall. He showed you the calculation. It's a tedious thing to look at. And second of all, it's going to be an approximation. It's not going to be exactly equal, but approximation is good enough. All right. So I just want you to appreciate that. When I tell you the parameterization, you'll see, that's obvious. But the work that goes into like verifying it, right, is non-trivial. That's all I want to say. So the right parameterization is U will be e to the sigma square root of delta t, and D will be sig e to the. So D is just 1 over U. Okay. Notice is, first of all, it's kind of symmetric in that way. And second of all, right, when you plug in, right, these choices, you will get approximately that the return, right, is risk-free, and volatility, let me just do one return, okay, is approximately sigma squared. All right, so meaning, like, you know, these are the equations I wrote up here, right? Like when you plug in, you get approximately this kind of thing. Okay. So yeah, and I just show you by calculation, right? But so that's also a beauty of, right, coding, right? With coding, we don't have to go through the the abstract verification. If we just try a few, and that's not a proof, right? But at least we can see that that's sensible. And actually, I think somehow it's also more enlightening. All right, so that's the first thing that I want to talk about, the parameterization. All right, quite important and quite practical. Again, right, especially like I said, when you want to do real work, right, when you want to look at like more complicated option like American exotic, I would claim that modeling under UND makes no sense. Modeling under sigma makes much more sense, because then, right, the sigma will enter into the price of these options as well, rather than working with UND. Okay, I mean, again, that's for practical use, right? For theoretical discussion, UND are perfectly fine, right? For practical use, sigma calibration is much more meaningful. All right. Second is what I want to talk about this, right? So the conversions of binomial model as delta t goes to 0 and n goes to infinity. All right. So here I will wave hand a little bit, but I just want to give you a flavor of things. So basically, right, the key idea behind this is central limit theorem, which says something like this, right? The central limit theorem in the classical version says that if you have x1 up to xn IID with mean mu and variance sigma square, then you have x bar, which is the average, then x bar minus mu divided by sigma over root n is approximately a normal distribution for n large. Okay, so that's central limit theorem. But when you look at, right, the situation we're in the binomial model, you won't see this so much. Okay, so let me tell you a similar version, but that will be more useful for what we're doing. A second version is like this. The second version is this, that x1 up to xn are IID. But here, so notice that here as n changes, right? As n changes, the assumption is the x have the same distribution as originally. So it doesn't matter what the sample size is. These guys have the same distribution. In this context, as the sample size change, the distribution will slightly change. The reason is I will scale it like this. The expectation of the sum will always be mu, and the variance of the sum will be always sigma squared. All right, does this remind you of something? Anyway, right, so notice, so what am I saying, right? I'm saying that, so notice that these guys would definitely change with n, because as n increase, right, I'm basically scaling the mean down, like mu over n. And I'm scaling the variance down like sigma squared over n, right? Obviously, if I keep the same sequence, they won't behave that way. But if I could do this, basically I scale each random variable as I go down, then the sum itself right? This is no surprise. It's approximately normal with mean mu and variance sigma square as n goes to infinity. Right? So here the scaling is done by taking the average and then divide by this. Here I say that implicitly the scaling is done within the variable itself. Okay. Now, why is this version more useful to us? Can anyone tell? Because that's exactly how log return behave, right? Log returns add, and doesn't matter how you make the delta dt small, the sum, right, on a fixed time interval will always have the fixed expectation and a fixed variance, fixed time, right? So think of course, when you have a fixed option, then of course exploration is fixed, right? So think of t as fixed. Then and dt, right, the time interval will be smaller and smaller. Does that make sense? So think of it like this, right? So basically, each time you have a very small up and down corresponding to each time period, like that, right? Then the log returns will always add, so it will keep fixed, and variance will always also add, so it keeps fixed. So the point is, right, if you do it like this, because the log returns add, and as the delta t gets smaller, right, you get a lot of log returns adding up. The effect is overall, by central limit theorem, your log returns, right? So think of this as your log returns, okay? Over a small time period, like daily or something. So the point is, right, as you keep adding these small log returns, they will accumulate together like a normal distribution. They will accumulate together like a normal distribution, okay? So if you add a bunch of small log returns, they'll accumulate together like a normal distribution. And that will give you a Brownian motion, because Brownian motion, right, is basically any time interval. Between any time interval, you got a normal distribution. And I just want you to appreciate the fact that the normal is because between S and T, you got a bunch of log returns adding up, where you keep the mean and the variance fixed. So that's why it accumulates into a normal distribution by the central limit theorem. Question? So, right, appreciate this if you can, right? I just want to tell you that. Now let's take a look at the code. Let me see here. Oh, Fatime was asking question. Sorry, Fatime. When I do this, I don't see your chat. All right. So if you have questions, send me an email later on. All right. So let me see here. Let's go to Canvas. Python files. Okay, what do I want to show you? I want to show you binomial distribution. I think here. Oh no, not this binomial model. All right, can I make it full screen? Anyway, can you see this all right? Okay, right. So first of all, right, here, this is exactly the piece of code that demonstrates to you that when I choose, right, u to be e to the sigma square root dt, and d is 1 over u, then, right, the rate of return Notice I do risk neutral, right? This is E to R delta T minus D over U minus D, right? Then to find the rate of return, right? I take this and divide by the interval of time, right? I got 0.02. What is 0.02? That's the R parameter I'm setting, all right? And notice, so what am I changing here? I'm changing the time period to be smaller and smaller, right? So the approximation will be more and more precise. So notice like this becomes closer and closer to R. And notice how the sigma square, right, is closer, sorry. So here, right, for the volatility, I already take the square root, I believe. Let me see here. Yeah, see, I took the square root already, right, of the variance, right? Notice this is the fancy variance divided by dt, right? And I took the square root. So, right, see how it gets closer and closer to 0.3. So this is the, of course, you can rerun this code for any choice of sigma and any choice of R. You'll see similar results. All right, I am not running Python up here, so I just show you this result, but got it? So that's the demonstration that the parameterization works. Remember, I told you to check the U and D when you plug in, you get the right sigma square, right? This is the one. Now, the next piece is this, right? The next piece is an interesting piece where now I claim, right, volatility is the same whether you use physical or risk neutral. So what does physical probability mean? Who knows, right? There's no definition of physical probability. So I just use 1/2. Okay, 1/2 is some other probability and redo the calculation. So what do you see? Notice the return change now, right? Return is higher, is 4.5%. Yes, but volatility stays the same, even if I use 1/2, which is not risk neutral, right? So this is crucial, right? It's a very important fact that volatility is the same under risk neutral or under physical probability, which kind of makes sense because you know what? Say we calculate implied volatility, right? And someone say, well, you compute it under the implied volatility, under the risk neutral framework. But we live in the real world, right? If somehow transitioning from risk neutral, right? You know, something doesn't stay the same. For example, right, return doesn't stay the same. If volatility doesn't stay the same, then the calculation you've done under the implied framework doesn't mean anything under the real world. Then what's the relevance? But here, right, it shows you that, yes, the volatility stays the same. So the information you get from implied volatility is applicable in the physical world that we're living in, all right? Now, sometimes it doesn't translate, right? And you have to think of how to interpret. And that's actually the tricky thing in pricing. People sometimes will question you. You're doing this under the risk neutral, but we're living in the physical world, okay? What's the relevance? For example, a lot of times you calculate, we won't talk about this, but you calculate default risk of default, and you do it under risk neutral. But we live in the real world, right? You tell someone that this guy has a risk of default of 5% under risk neutral, but you want to know how much he will default in the real world, right? So that won't work, for example, right? So okay. Anyway, so that's these two. Any questions so far about these two pieces? All right. So now the next one is the conversions of binomial to Black-Scholes. Okay. And so here I just want to do it pictorially in the sense that, right, here I simulate again different path with different dt, the same dt as above, right? 3 choices. And then, so this is the simulation of the binomial model. And then down here, I simulate the Black-Scholes model. Notice I use the normal, right, distribution down here. And then I use the binomial distribution up here. All right. And so you can see, for example, right, as the dt increases, notice how the path becomes like this, right? Much more fluctuating, right? So this is a typical, right, binomial path, and this is the path when dt is very small. Now this is the Black-Scholes path. Of course, they're not the same because I'm not, looking at them from the same sampling, but look at the qualitatively how they're the same, how they're very similar. All right. So that's what, at least hopefully this, right, shows you that, okay, that as dt you push to very small dt, you get something that, well, mathematically it will be, right, a normal distribution, but pictorially you see they behave in similar way. All right, questions so far? Okay. So I think let's show you Black-Scholes model. So here, the next thing I want to show is like this, right? So after today, we'll start to talk about Brownian motion and stochastic calculus. And so, right, I want you to understand, right, the connection between binomial model and Black-Scholes model. But but underlying that, right, do remember that, like, the Brownian motion is the random source, okay, of Black-Scholes model, not Black-Scholes model itself. So it's like one is e to wt and one is wt. So I want you to remember that it's random walk that converges to Brownian motion, okay? Not the binomial model. The binomial model does not converge to Brownian motion. The binomial model converges to something like e to wt. All right. So here I just kind of redo the simulation, but show you random walk itself, right? That converges to a Brownian motion path. Now, what's the difference? A Brownian motion path always starts at 0. The stock price starts at S0, as you see, all right? And the notice, right, also here, remember how, right? So actually, because mu is 0 for the random walk, that's why the random walk kind of on average fluctuates around 0. But remember how variance grows with t. So this is like the return in some way. This is the return, but you subtract away the mu. So the mu is kind of at 0. Right? Notice how as time goes out, right, the fluctuation becomes further and further. So this is variance grows with t kind of thing. All right. But here again, it's just demonstrating, but kind of show you or ask you to differentiate, right? It's important that random walk converges to Brownian motion, okay? The binomial model converges to e to wt, okay? Exponential Brownian motion. Then here, to be careful again, right? I want to show you. Here's the Brownian motion path, right? The stock price looks very similar to the Brownian motion to the naked eye, but they're different. Why? Because again, one starts at 0, one starts at 100. Okay. Second of all, right, the stock price actually has the mu minus 1/2 sigma square. So this is the exponential. But right, again, to the naked eye, notice, but it kind of makes sense because, right, this is the random source of this guy. Right. So when you exponentiate it, qualitatively, the path still looks very similar, right? But just to kind of distinguish this. Okay. And the last piece, which you will use later, I'll talk about it now. The last piece is about Monte Carlo simulation, or just simulation in general. Does anyone here know about Monte Carlo simulation, or at least the idea of it? Yes, no, maybe? All right. So the idea of Monte Carlo simulation is this, right? It's very simple. If you want to calculate expectation of something, you just generate a large sample of that thing and take the average. That's all. What's the benefit? The benefit is you don't have to go through the analytical formula to derive what the actual integral is, right? You just let the computer do the work for you. What's the disadvantage? The disadvantage is sometimes the conversion takes a long time to happen and you get an approximation, meaning you have to simulate a lot of sample to get a good data, good result, right? So here I just want to show you an example with Black-Scholes, right? So two things. I calculate Black-Scholes by theoretical formula by plugging this Coll-BS formula, right? By plugging this Coll-BS formula. So that's a theoretical price. for the simulation price, what did I do? Right, I just simulate a bunch of ST right here, right, with I don't know, 1 million sample, and then I take the average. And you see how they are kind of close. But right, do know that the top one is the right one, the exact one. The bottom one, right, is the simulation one. And again, I am not on Python here, so I cannot show you, but if you reduce it down to 1,000, then this guy, the second guy, will be very, very awkward. The second guy will not be precise at all. It will be jumping around a lot. Okay, so only at about, I think 1 million is a little bit overkill, but like 10,000, 100,000. Okay. But again, right, notice that for the second guy, I don't need to go through Black-Scholes formula. I just do this. I just generate the stock price using my model, and then I average. Is that okay? This is very useful because when you run into something that is much more complicated to calculate analytically, then right, simulation is your way to go, at least before you can figure out the analytical calculation. And we'll do a lot of that in this class, hopefully. Question? Okay, cool. So let's go back to the lecture. All right. So any question on the Monte Carlo simulation thing? Everyone got the idea okay? Or you want me to explain a little bit more? Anyone? Don't be shy. I don't want to say something that's boring to you, but if you want to, seems okay. All right. So let's go to right. So I guess I'm now kind of done with the background, right? I have talked about the things I want to talk about in terms of modeling, meaning of pricing, that kind of thing. There's one thing I didn't talk about, is risk neutral, right? What does risk neutral mean? But we'll talk about that when we come to that part. So for now, for the next few lectures, I think we're going to do it a bit more theoretically, all right? So now kind of Math Finance 2 proper in some way. It's going to be Brownian-Motion and stochastic calculus. And right, I think we've talked enough. So I hope you understand the motivation of this, right? Black-Scholes model is built by Brownian-Motion. So we need to understand what Brownian-Motion is about, at least a little bit. What is Brownian-Motion? We'll define it mathematically, but you can also think of it as the limit, right, of symmetric random walk as the step size gets small, like in the simulation. That's why, again, right, Wall Street loves to say that it's a random walk, stock price like random walk, etc. It's not true, right? Stock price is like exponential random walk. I mean, or it's not precise, right? Stochastic calculus, why do we need to study it? Because stochastic calculus is exactly the piece that connects, right? These things, right? These three pieces are connected by stochastic calculus, all right? And even more fancier, right, analysis we'll use stochastic calculus. So anyway, so first, right, let's define Brownian-Motion. All right. So now, right, I don't have to tell you, but T now is continuous, all right? So T is no longer discrete, and let me say so, from 0 to big T, let's say. So W as a function of T, all right, is a Brownian-Motion if it starts at 0, it has independent, I'll say this, IID increments, and 3, the increment is distributed like a normal distribution. All right. So these three pieces uniquely identify a process called a Brownian-Motion. It's a very interesting way to define a process, and we don't have time to go into this, but if you ever take a course on stochastic processes, or which Professor Larson might have drilled you on it already, I'm not sure if he emphasized the point that defining a process in general is tricky business because you have to give all the finite dimensional distribution. If you ever heard of that. So basically defining how all the pieces connect together at different time points. In other words, you need to tell how the let's say T1, WT2, WTN interact together, meaning the joint PDF for any collection. All right. You need to know this information in order to say that you understand the process. All right. Why? Think about like stock, for example, right? If you want to analyze a stock, right? You don't want to analyze a stock at only one time point, right? You only do that if you have like, a European option. If you analyze anything like a path, then you want to know, right? How does the stock on different period, right? That you sample, how do they interact together? Does that make sense? Because one guy may influence the other, right? In different ways. So you want the joint distribution, understand? So that's what you always want with a stochastic process. You want to say, if you sample, right, this process at different time points, how do they all interact together? Let me give you some example, right? You probably want their expectation, which is fine. But next thing you want is their covariance matrix, okay? Covariance matrix is a very standard object that you look at in, I don't know, machine learning, data science, whatever. What's covariance matrix? Covariance matrix is looking at the correlation or covariance, right, of each of these pair of these guys. So that's the joint behavior again, right? Why do I say this? I say this because, right, that's what you would want to have for any processes. But mathematically, it will be impossible, right, to define this for any collection. You want a simple way to capture it. And believe it or not, these three pieces capture this completely. All right. That's the beauty of this definition. And it all hangs on this ID increments. All right. So again, right, I could go to the math, but I feel you guys benefit more, for practical understanding. So I just want to mention this, right? And if you're interested, you can go look it up yourself. But I'm just saying that this is not a trivial, right, definition. It has some meaning behind that. All right. So now, all right. So let's unravel this, right? So this is standard, right? So basically, let me tell you that you don't have to start a Brown motion at 0, right? You can start a Brown motion at any time point. How do you do that? You add a constant, right? Then you just shift it up or down. So this is kind of conventional, doesn't matter. But people usually think that if you don't say anything, it starts 0, right? Let's talk about this guy. What does this mean? The second piece means that if you have non-overlapping time period, let's say this, right, non-overlapping, then WU minus WT will be independent of WT minus WS. All right. And right, this is called increment, meaning the change, right? Notice that this is what we kind of mean by DW. But this is DW, right, from T to U. And this is DW from S to T. All right. Now, I do this because I want to highlight that even if the time, kind of, right, has that one point, kind of touching, but more generally, S less than T less than U less than V, then WV minus WU is independent of WT minus WS, right? As long as the time interval is non-overlapping, the behavior has nothing to do with each other. So, right, what they're saying again is something like this, right? It's the picture I draw, but whatever. So S and T here is U and V. So basically, right, if you look at how W, right, change from here to here, that knowledge doesn't help you in any way in predicting or thinking about the knowledge of the movement from here to here. All right. Now, what does that remind us of? Returns again, right? It's exactly this behavior that kind of captures, right? If you know the return of this month, that gives you, at least in theory, right? It gives you nothing about, right, the return on, let's say, that the next month in the future, right? You cannot say anything knowing the return of the stock this month, right? Okay. What else, right? So that's the independent part. The identical part is basically this, that if the length of time is the same, okay, if t minus s is equal to u minus v, if the length of time is the same, then the distribution is the same. All right. So what this is saying is, like daily stock return have the same distribution. Monthly stock returns have the same distribution, right? Well, of course, right, we will build return out of Brownian motion, right? Right now it's just Brownian motion, okay? And then, so notice why, right? Why piece number 2 is almost like the defining piece. The reason is this, right? A process value can be built out of its increments. Okay. Sorry, okay, I have 4 minutes. What does this mean? It's very simple. What it means is like this. So it's actually the same trick again. Let's say we have a WS here, right? Then what's WT? WT is WT minus W0, right? Because W0 is 0. But if not, then you just add the original timing. Then what is this? This is going to be WT minus WS plus WS minus W0, right? So this is the increment from S to T plus the increment from 0 to S. Does it look familiar? This is exactly how you build the returns, the stock price from the returns, right? So anyway, right? So why do I say this? Because, right, if you want to know the process itself, right, this is the value of the process. But what I'm saying is, if you can control the increment, and you can rebuild, right, the original value out of the increments. So if you know the increments, you do know the process itself. That's why the IID increment is key to control, to know the information of the process in this case, right? Now, we'll get to this later, but actually the concept here is the formula is this, right? I'll write this. What we're writing is something like this. This is what we're getting. I don't know. Formula number 1 of stochastic integration. So we will talk about Ito integration, Ito integral, right, later on. But it starts out with something as simple as this. What am I saying? Well, I'm saying that notice like the integral here is just continuous adding, all right? If I continuously add all the changes, what do I get? I get the big change, which is something like this, right? It's just pushing everything to very, very small. Does that make sense? So what I want to say is we'll learn how to integrate Brownian motion, right, against Brownian motion. But at the base, at the heart of it is something as simple as just telescoping something. All right. Now the last thing is this, right? That you still. So now, first of all, right, you can reconstruct a process out of its increments.
But if you don't know, so of course, right, you know how this works almost, right? You know they're independent. So that gives you the joint distribution. But you need to know exactly what this piece is, right? Otherwise, how do you know what this is? How do you know this? This is from piece number 3. So piece number 3 gives you the identity of the building block, right? They say that the building block must be normally distributed. All right. So now you would know that, for example, that this guy is a normal 0 t minus s. This guy is a normal 0 s. Right? And now you add this up. Now, if you add in the independent normal, what do you get? You get normal, right? You get independent normal, you get normal. So there you go, right? So now you know WT has normal distribution from the increments. Okay, so I think time's up. So the point is, right, we'll pick up this next time. But now, so right, so we'll start to play with Brownian motion and talk about all the properties and build up stochastic calculus. But the point is this, right? For the Brownian motion, and this is the point of calculus. Calculus means that you build the process out of the derivative. All right, I'm not sure you realize that's the point of calculus. But that's the point of calculus and differential equation. You rebuild the original function out of the derivative. What's Newton's mechanics? Newton's mechanics says F equals to ma. Why? Because a is a second, right? The acceleration. Now, when you look at an object, you don't really care about acceleration so much. You care about what? You care about the position. You want to know where it is at a certain time. But Newton's mechanics cannot describe the position easily, right? When an object is falling, how do you describe the falling position? Well, you say that the acceleration is constant. And you rebuild, right? You integrate twice. That now you can say position is a square function of time. Got it? So that's the principle. All right, that's the principle of calculus. And here we do the same thing, except that we do it stochastically because our piece is random. So it's stochastic calculus. All right, so see you next class. So we got this working. So hopefully see some of you next class to help me run this. But otherwise, right, we're going to stay flexible. If the university says something, right, if they complain, back you go, all right? But if it's up to me, I don't care. You too. All right, Fatima, you're good? Any question?
You emphasize that T minus S equals V minus U. I just don't know why you emphasize this.
Oh, that's the identical, right? IID.
Yeah, because we say identical, must be in the
So-
equal time span.
So when are two random variables are equal or identical, right? Two random variables are identical if they have the same distribution, but they also should have the same mean and same variance, right? So a normal 0,1 is not the same as normal 0,2. Do you agree?
Yeah.
So because the WT minus WS is normal 0 with variance T minus S. So unless the variants are the same, I cannot exactly say they're equal, right, in the distribution. So that's the only thing. That is really normally distributed, but if you have different length, for example, if you think of return of the stock on a daily basis compared to a month, are they the same? You can look out, thank you. They're not the same, right? They might have the same distribution, but they're not the same in terms of the scale.
Yeah, because we can consider it have different time, different
Length.
yeah length, and we don't get a same amount of
Variance.
Yeah. Yeah, so we need to control the.
So that is to be precise when we say identical, right? That's what we mean.
Yeah.
But if not, then it's still similar,
Yeah.
but scale-wise, right? It's not the same. That's why we have to emphasize that to make it precise on what we say,
Yeah, it makes sense. Thank
right?
you.
All right, Fatima, what question do you have? Yes, from the three items, you can deduce the joint, right? There's some work there, but because now you can break, right, those W into their increments, and then, right, deduce the joint by the joint of the increments. Does that make sense? So that vector, right, now you can break it down to the increments, and then rebuild it, and then compare them, right? It's some work, but that's exactly how you do it. You understand? All right. So I think I have to run because there's some people trying to come in. Feel free to send me an email, all right? I'll answer your question. All right, cool, thanks.